Hi everyone, I'm Adil from Purdue. Today I'll be previewing the operating system and hardware sessions at OSDI and ATC. So this year we have a fantastic lineup of papers, and they're primarily centered around the three important duties of the operating system, namely process scheduling, memory management, and network management. Whereas some papers will talk about ways to improve the existing hardware. So let's dive right in and talk about process scheduling, which is the important duty of the operating system where the OS gets to decide which process is going to run on a certain CPU at a certain time. Now, related to process scheduling, there are two important concepts. The first is that of fairness. The operating system should ensure that each process is allowed to use the CPU equally so that each process is able to do useful work. The other important concept is that of latency. The operating system should empower each process to complete as soon as possible and efficiently utilize hardware resources. The first paper in the process scheduling section is going to talk about how AVX instructions actually cause scheduling unfairness and what we should do about it. So AVX instructions are, let's look into what AVX instructions really are. Well, we know that normal instructions actually process data in chunks of 64 bits because they have access to 64-bit registers. Now, AVX instructions have access to larger registers which are 256-bit or 512-bit wide. As a result, AVX instructions are able to process more data at the same time. And this results in better performance for certain applications. Now, unfortunately, AVX instructions also end up in contributing to scheduling unfairness. And the reason for that is that AVX instructions force a CPU core into a lower clock speed. And this is primarily because of hardware thermal limitations. And as a result, the CPU is forced to run at a lower clock speed compared to if the CPU was only running non-AVX instructions. Now, this is fine because AVX processes are going to benefit from the higher performing AVX instructions, so lower clock speeds are still okay. However, we see that non-AVX processes that are running alongside these AVX processes are also going to be affected by these lower clock speeds. For example, in this one particular case, a process is running on a hyperthread next to a process running AVX instructions, and that process is also forced to run at a lower clock speed, and that is unfair. So this paper talks about how we need to identify these scenarios of unfairness and compensate the affected process. The second paper is going to create a scalable hybrid event queue to reduce the application latency in Linux kernel. So what exactly are event queues? When an event, for instance, a network packet is received by the operating system, the OS first buffers the packet in a certain queue and waits for a thread to be free and then sends that packet on to the thread. Now, unfortunately, we see that the existing model of event queues actually result in significant latency. So there are two existing models of event queues in Linux, the first of which is the one-to-one model, where we have each CPU thread being allocated a certain queue. And when an event arrives, the OS decides which of these queues an event is going to be buffered in. Now, the problem with this is that we run into underutilized CPUs because once an event is buffered in a certain queue, it's very expensive to move it to a different queue. As a result, the operating systems don't really do that. The other model that we have here is the one-to-one model. Now, this model has one shared queue for all CPU threads, and whenever we're dequeuing a packet, we figure out which CPU is currently free, and we just simply send that packet or the event to that particular CPU. Now, this results in good utilization, but unfortunately, you now have to synchronize amongst all threads on the CPU, which again degrades performance. So this paper talks about how to implement a new scalable event queue that is a hybrid of the one-to-one and one-to-one model. Now that we've talked about process scheduling, let's move on to memory management, which is the other important duty of the OS, where the OS must allocate the memory to certain applications. Now, Concerning memory management, there are two concepts that we should recall. The first is that of memory conservation. Now, the operating system is going to try to make sure that it can support as many processes as it can, thus it will try to conserve the amount of memory it uses. The other important concept is that of maximal performance, where the will actively try to reduce the performance impact of memory accesses for certain applications, for applications. The first paper in the memory management section concerns with huge pages, specifically creating a new memory allocator that is optimized for huge pages. So what exactly are huge pages? To understand them, we also need to recall how translation works in modern CPUs. Now, a process is allocated virtual memory. Now, the virtual memory is translated into a physical memory using page tables that are created by the operating system. Now, since page table based translation is very slow, modern hardware implements a cache which it calls the TLB, and the CPU tries to perform translation as much as possible using the TLB because it is significantly faster than going through the page tables. Now, this is problematic because in normal scenarios, we have pages that are only 4 kilobyte in size. And that means that each 4 kilobyte page must now have its own TLB entry. And since modern systems have gigabytes of memory, we would need a huge TLB and many TLB entries to support these normal pages. So as a result, what we have is the concept of huge pages, where instead of translating at 4 kilobyte granularity, we simply try to translate at 2 megabytes granularity. And as a result, we need fewer TLB entries. And this results in better performance for certain applications compared to normal pages. Now, there is no free lunch. When we use huge pages, we run into the problem of memory fragmentation. Consider this scenario here where you have 4 megabytes of memory and the process asks you to allocate 2 buffers of 2 megabytes each. Now, this memory is completely used and that's fine, but let's say after a certain time, the process frees 1 megabyte of memory from each of the existing 2 megabyte buffers. Now, potentially you have 2 megabytes of memory free on the system, but if the process asks you to allocate a 2 megabyte buffer, you simply won't be able to because that memory is now scattered in different chunks on your memory on your memory inside your memory region. So this paper talks about how this problem of fragmentation should be dealt with by a new memory allocator that is aware of such scenarios and tries to actively minimize them. The second paper is going to discuss how to design a new operating system kernel that is optimized for server NUMA architectures. So what exactly is NUMA? Well, NUMA architectures are these new server architectures where you have multiple sockets where each socket has its own CPU and its memory. Now, these sockets are connected to each other using a slow interconnect, and the CPU can access both memory regions that are local and remote to the socket thanks to this interconnect. However, since the interconnect is slow, the memory access speed now depends on the locality of access. So accessing the local DRAM is faster than it is to access memory on the remote DRAM. The problem with this is that existing kernels like the monolithic Linux are actually not optimized for NUMA architectures because they were designed in times where NUMA wasn't a thing. So existing kernels like Linux have a shared kernel state which is accessible to all CPUs. As a result, what we see is in NUMA architectures, because multiple CPUs on different sockets will be accessing the shared kernel state, the kernel state will actually be divided into different sockets. And because the kernel state is frequently accessed, a CPU would have to frequently access the remote DRAM to access the kernel state that is located in that remote DRAM. And as a result, we see significant performance degradation. So this paper talks about how we need to design a new operating system kernel that actively tries to reduce this sharing of kernel state amongst different sockets to optimize performance. The third paper in the memory management section is going to explore new page management designs for multi-tiered memory systems. So what exactly are multi-tiered memory systems? We just saw NUMA architectures where we have multiple sockets with multiple DRAMs. And now what we have is a new sort of a memory hardware, which we call a slow memory or a slow DRAM or a DC persistent memory. Now this is a hardware that will be when it comes to NUMA architecture, this slower memory will now be on each socket of the machine. And as a result, accessing a memory will not only depend on whether you're accessing it locally, but it will also depend on whether you're accessing it at a faster memory tier like the DRAM, or you're accessing it from a slower memory tier like the DC persistent memory. And unfortunately, because the multi-tiered memory architectures are still relatively new, the existing Linux kernel isn't optimized to consider these scenarios properly. For instance, consider this one scenario here where a CPU is allocating a significant amount of memory and the local DRAM is now full of data. So in this particular scenario, the operating system like Linux will try to optimize for locality. And as a result, it would keep that data in the local slower memory tier to preserve that locality. But in fact, Linux should actually be migrating that data to the remote DRAM because accessing the remote DRAM is still faster than accessing the slower memory tier. And this is a scenario that Linux doesn't consider. So this paper talks about how to consider these scenarios and to implement a new page management scheme that implements this migration. The third section that we're concerned with today is that of network management. And concerning network management, there are actually two concepts that are extremely relevant, especially in data center networks. The first concept is that of short flows and long flows. So a flow is just a stream of network packets. And flows can be short. For instance, they could be web requests that are only a few kilobytes generally. Or they could be long. For instance, they could be database snapshots that could range from megabytes to gigabytes of network flows. The other important concept to remember is that the short flows are extremely latency sensitive, so they should be prioritized over long flows to reduce the overall latency in data center networks. Now, the paper that is concerned with that's going to talk about network management is actually going to implement a new network transport protocol, which is called the Homa transport protocol on the Linux kernel. So let's understand what the Homa transport protocol is, but for that, let's first look into what normal transport protocols like TCP do. So in TCP, a sender has no control over how the packets are handled within the network. So as a result, what really happens is that there could be a router queue where a short flow is enqueued behind a long flow. And this is not optimal for us because the latency sensitive short flow would actually be delayed significantly. And this is a grave concern in data center networks. So what Homa does is it allows the sender the ability to configure how the packets will be queued inside these routers. And it allows the sender to configure the priority queues inside these routers. As a result, what would happen is that the shorter flows will now be inside a higher priority router queue, whereas the longer flows will be in a lower priority router queue. And the short flows will be explicitly prioritized and their latency will be reduced. Now, unfortunately, when Homa was introduced, it wasn't tested in many practical settings. Its evaluation mostly consisted of simulations through software network simulators, and its implementation was also user level, and it involved a kernel bypass, which means that it wasn't including many of the overheads that the Linux kernel would add to a transport protocol. As a result, this paper implements a new Linux kernel-based implementation of Homa to allow fair evaluation of Homa with existing transport protocols like TCP. The final section is going to concern with new ways to improve the hardware, particularly to particularly improve the security of remote computation, for instance, computation on untrusted cloud machines, or improve the performance in many emerging real-world scenarios. So the first paper in the novel hardware design section is going to talk about how to create a new enclave that is more scalable and robust than previous enclave solutions. So what exactly is an enclave? Well, normal programs are completely visible to the operating system. And this is a problem because the operating system can now extract whatever it wants from the program. This is generally fine because we trust the operating system, but in certain scenarios where we're doing remote computation, we don't trust the OS. And as a result, this is not good for us. So modern CPUs allow a certain programs to create what we call an enclave, which is a protected memory region that is not visible to the operating system, and the OS cannot extract contents from the application. Now, moving forward, enclaves are also encrypted when it comes to the main system DRAM, and as a result, the good thing is even if someone has physical access to the machine, they still won't be able to extract your sensitive contents. Now, unfortunately, the existing enclaves just do not scale. For instance, SGX, which is a very famous enclave system, only supports up to 256 MB of memory in most CPUs that it is offered in, and that's not suitable for many scenarios. The other problem is that existing enclaves actually take many seconds to boot up, and that is problematic in emerging scenarios like serverless computing, where you want to create a serverless instant in microseconds. So as a result, this paper is going to talk about how to implement a new enclave system that is more scalable and is faster than these existing solutions. The second paper is concerned with creating a hardware-based virtualization for computational storage devices. What exactly are computational storage devices? Well, a computational storage device is simply an FPGA and an SSD that are merged onto one device, and now this device can now be plugged into your main machine using the PCI Express interface, just as we plug other things like graphic cards on the machine. Now, the good thing about this is that we can now offload much of the computation that we want to do on the SSD directly to the FPGA, and the computational storage device can do all that computation and only return us the output. So as a result, we don't have to move a lot of data through the slow PCI Express interface. Now, since computational storage devices are also relatively new, their virtualization involves a lot of software components. The reason is that computational storage devices do not have any support for hardware virtualization currently, so they have to rely on software para-virtualized instances of these computational storage devices that are created by the hypervisor. And these interfaces are extremely slow. So this paper talks about a new hardware design that allows direct virtualization of computational storage devices from each virtual machine. The final paper in this section is going to talk about how to create a nanosecond network stack that is suitable for data center networks. So in data centers, what the remote procedure calls are very common. So what exactly are remote procedure calls? Well, a remote procedure call is if a function called a function on another machine, just as if it was calling a function on its local machine. And the way that this works is that the OS abstracts away all the network stuff, so the processes think that they're just calling a function on their local machine. Now, remote procedure calls are very common in data center networks, as I mentioned, and they are becoming more and more short-lived. For instance, they only live for a few nanoseconds to just a single microsecond in many scenarios. And existing network stacks are just too slow to keep up with with these very short-lived remote procedure calls. So the existing network stacks we have the software stacks like Linux, which can take up to hundreds of microseconds to answer a single RPC. And even the existing hardware stacks such as RDMA still take 1 to 2 microseconds, which is still too long for these very short-lived RPCs in data center networks these days. So as a result, this paper talks about how we need to design a new network stack from ground up that allows us to serve these 1 nanosecond requests. So to conclude, we have a fantastic lineup of papers this year at OSDI and ATC, and I for one am super excited about these talks. So I hope to see you all there. Thank you and bye.